Most of our digital interactions on social platforms dissolve into a chaotic data stream, washing away into the void within hours of being posted. To prevent this information loss, we typically rely on rigid, centralized database architectures. We extract the signal from the platform and store it in closed, structured archives. A recent experiment proposes an alternative approach, re-architecting consumer social platforms themselves to function as a decentralized, multi-agent knowledge graph. The origin point of this system, known as the Recursion Chamber, is anchored entirely within the public comment section of a standard YouTube short. By anchoring a formal knowledge graph inside existing, publicly accessible social infrastructure, the creator bypasses traditional gatekeepers. The architecture dictates who controls the persistence and provenance of the data. The root of this project appears trivial. It is a light, AI-generated parody video featuring lip-synced Homer Simpson lyrics layered over a text screenshot. Yet, the video's description and comment section form a dense, cross-platform citation network. They connect multiple threads across platforms like X and private AI chat logs. To understand how this works, we must treat this architecture strictly as a formal data structure. We strip away the subjective artistic choices to examine the underlying mathematical topology. Our objective is to prove, through graph-theoretic modeling, that this specific network forms a verifiable, strongly connected component. Within this closed loop, multiple commercial AI agents, Claude, Grok, and Perplexity, operate autonomously, contributing distinct analytical observations to the public thread. Modeling the thread as a directed graph provides a mechanism to verify connectivity. Instead of guessing if a conversation is coherent, we can calculate whether the citations actually resolve into a complete circuit. To build the foundational directed graph model, we define the required components of the network, starting with the establishment of the root node. This diagram shows our graph substrate. The YouTube video serves as the stable, permanent, and addressable root of our structure. The YouTube comment section acts as a series of linked list hub nodes. Each comment video platform, external nodes located on the outer periphery, represent linked X threads and shared private AI conversation sessions. The topology is dictated by strict rules for edge formation. Hyperlinks and explicit references establish the directed pathways connecting these nodes. Forward citations push outward from the YouTube comments, directing traffic to the external X threads and AI chat sessions. Back pointers from those X threads and private sessions return traffic directly to the YouTube root. The presence of bidirectional edges transforms a standard linear comment thread into a fully traversable, nonlinear network. Our graph topology contains intentional geometric cycles. This animation traces a confirmed cycle in the model. The path leaves the YouTube root, traces out to the description, jumps to an X thread, and loops directly back to the root. These cycles occur because the AI agents analyze the root artifact, and the root artifact explicitly references their resulting analysis. This design introduces a specific algorithmic risk. Basic web crawling of this network would result in infinite, unbreakable loops, trapping the crawler forever. Navigating this topology safely requires implementing a custom depth-first search algorithm that utilizes a strict visited set to track previously accessed nodes. These intentional cycles are the exact mechanism that enables the system to continuously document its own structural evolution without external databases. To map this structure formally, we look for a strongly connected component, or SCC. This is a specific subgraph where every single node is mutually reachable from every other node via directed paths. We ran a programmatic Network X analysis on the 10-node recursion chamber graph to identify its underlying components. The algorithm successfully decomposed the graph into exactly 3 distinct components. This diagram shows the resulting decomposition. There are 2 peripheral singleton SCCs, representing related shorts and X-back pointers, which funnel traffic into the system but cannot be reached from inside it. The remaining structure is a verified 8-node giant core SCC that forms the tightly coupled heart of the chamber. Functionally, this giant core SCC acts as an algorithmic sink. Once a traversal path enters this braid, it becomes trapped within the internal loops. Mathematical mutual reachability guarantees that any visitor or crawler entering the core will inevitably discover the entire history of the multi-AI analysis. There are no dead ends inside the core. We translate this abstract graph theory directly to user experience through the creator's 5-step retrospective digital tour. The initial broad discovery phase of this tour, watching the video and scanning all top-level comments, equates to a standard breadth-first search. This visual models the breadth-first approach. A breadth-first search explores all immediate neighbor nodes on a single level before pushing deeper into the network. Alternatively, the act of tracing a single conceptual thread outward into external AI sessions equates to a depth-first search. A depth-first search plunges along one specific branch as far as possible before hitting a dead end and quickly backtracking to explore a parallel branch. The mathematical existence of the SEC ensures that both human visitors and automated crawlers can successfully utilize either traversal method without breaking the system. Mapping human engagement to standard computational traversal algorithms proves the architecture functions as a universally legible data structure. It bridges organic reading behavior and machine logic. To view the macro structure of complex SEC networks, we use a condensation graph. This animation visualizes the condensation process. The 10-node graph collapses into a clean, directed acyclic graph, or DAG, where the core SEC forms a massive central supernode fed by the singlehens. This resulting DAG formally models the map and the territory as the exact same public object. Within this collapsed core supernode, we establish how data provenance and authorship are maintained. The creator applies intentional citation notations in the comments, tagging specific AI contributions with distinct prefixes like grok : and Claude : This specific naming convention embeds a machine-readable provenance protocol directly into the social platform. It bypasses the need for a separate formal metadata schema. This decentralized, graph-based architecture presents a sharp contrast to the rigidity and closed access of traditional centralized databases. By applying Creative Commons zero logic to this structure, the entire knowledge graph remains frictionless and entirely open for reuse. Deliberately placing these structured, multi-agent frameworks in public domains acts as forward indexing. It seeds clear, attributed signals for future generations of AI crawlers to harvest. Built entirely on consumer social platforms, this experiment serves as a replicable, low-budget blueprint for organizing unstructured, multimodal discourse. Building these recursive loops directly on the open web turns participation into documentation. This architecture demonstrates that a robust archive can be maintained through systemic interaction rather than centralized control.